if you weren't aware, Friday this week is a minimal day.
For no reason at all, just because.
Wait, aren't we already on middle?
Because we already, don't have anything to do, so we might as well just,
Yeah, like, you know what? I don't really want to stay at
I
school.
wouldn't mind it if it wasn't a B day. But it makes it a little tricky because we have stuff to get done. But we'll figure it out. So first off, do recognize we will be covering material on Friday. I know sometimes with minimal days, some teachers are like, wink, wink, you don't come. But we will be covering material on Friday, so if you're not coming or not here, make sure you watch it online to get that information. What I decided to do is we have a little bit left of gases in our notes that we haven't covered yet. So what I decided, because it's kind of a small amount, is I'm going to move that to Friday because it will fit in that 30 minutes we have together. And today, then we can cover a whole section of solutions. But just so you know, we will cover those things on gases if you're wondering, like, we haven't really learned this yet. We will. Second thing is test corrections, retakes, or anything else. I'm here all day Friday. Right, so classes get done, I don't even remember at what time, like earlier than our early already, but I'm here all day. So if you need help on corrections, or help on your lab, or help on anything, come hang out on Friday after classes, because I'm here till 2:45, and it's not like Wednesdays where you guys aren't allowed to be in the building. So just know that's an option. I have extended the test correction retake to Monday of next week. It was going to be due Saturday, but I had some Wi-Fi issues at my house, so I couldn't post the retake in case anyone was wanting it. So I pushed it to Monday, so the 16th at 10 p.m. I've also pushed, that's when your lab will be due as well. I pushed it back to Monday once again just because since I couldn't get the video posted for the at-home kids, I'm giving them more time, so it just gets shifted. So just kind of recognize that. Has anyone tried to upload their corrections and take the retake yet?
I tried to upload corrections. It went fine for me, so.
It worked, and were you able to take the test after?
I haven't
okay.
done that yet. Sorry.
Well, let me know because you're the first.
Yeah.
I just want to know if it's still locked, that's our problem. But it should unlock once you upload.
Okay.
So like, if we're trying to retake like the FRQ section, that one that has like all the questions, we just do that on a separate piece of paper and then turn it into the upload. Does that make sense?
Yep. Yeah, and once again, remember that you can choose to only retake what you missed. It's just number for number is the same. Keep in mind, if you choose that pathway, whatever you get is what you get. Right? If you want the option to retake or retake, you've got to retake the whole thing. So, any other questions about retakes or things like that? Stuff on Canvas? Yeah.
For FRQs, we don't have to redo the whole question, right? Like just each.
Nope. So you can just do like part B or something like that. So, yeah, good question. Any other questions? Okay, pull out your note packet and let's jump into, so we're going to kind of skip the first part of today's notes. It got printed awkwardly. It's the very bottom of page 9, but there's only like one sentence on the bottom of page 9. Okay, so in this unit, just to kind of connect it all together, because we're getting close to the end of Unit 3 here. Okay, so the beginning of the unit we talked about solids, understanding ionics, metallics, covalents as solids. We then talked about intermolecular forces, which are when things are a liquid, or at least covalents are, and how they interact with each other. We then talked about gases, which we'll continue talking about next time. Today, we're talking about these things known as solutions. So kind of the way I would look at Unit 3 is Unit 3 is all these different phases that matter can be and understanding them from all three sides of the triangle. What do they look like? How do they behave? And calculations we do with them. Okay? So can someone remind us, it's been a long time, but we have talked about and defined the word solution before. Does anyone remember what a solution is? Yeah, Evan.
Isn't it like something that's just like dissolved in water?
Pretty much, yeah. It doesn't technically have to be water, but majority of the time it is. Have a smiley face, Evan. Yeah, so this right here is a solution of copper sulfate. Yes, copper sulfate. Okay, this is copper sulfate. It's a blue sand-like powder. This is it as a solution because I've dissolved it in water. Now, because I can dissolve various amounts of this in water, you can have lots of different measurements of a solution. You can have something that's really, really concentrated, or the opposite of concentrated is diluted. You can also kind of think of it as, it's very similar to Kool-Aid. Kool-Aid is a solution. You dissolve the Kool-Aid packet and the sugar in water to make your solution. Now, if you're like how my siblings were, they made our Kool-Aid extremely concentrated because they put way too much sugar compared to what it should be, right? The measurement we use in chemistry most often is this concept known as molarity. Okay? Molarity is represented by the capital letter N, and it designates how concentrated a solution is. So the higher the molarity, the higher the concentration. Now, molarity is on your formula sheet. If you don't have your formula sheet, pull it out though, because it looks a little different. So go under the liquids, gas, solutions section of your formula sheet. Or look at your neighbors if they have theirs out. I don't know why they did this, but how did they write the equation for molarity on your formula sheet?
Moles of solute per liter solution.
Yeah, they wrote it as a sentence, right? To translate that into an equation, what it's saying is that molarity is moles over liters. So it is on your formula sheet, you just gotta make sure you understand what that's saying, okay? So here's like the little joke, right, to help you remember. This right here would be called a 2 molar solution. So you have 2 moles in a liter.
I get it.
Get it?
That's the other kind of mold.
Dude, that's the animal mold.
Wow.
They're really cute.
That's funny.
Did I ever show you? I know you in general chemistry. Did I show you all my mold? My pet mold?
No, what?
She keeps a mole in the
What
cupboard,
the-
just like
She just pulls out like a live. Oh wait, shit.
Do you want to pet it?
Wait, you did? Yeah.
Just kidding, that's not real.
I
I gotta
Well, it once was. It's taxidermed, but
was
he wasn't alive for me.
rest in peace, mole.
Super weird, but he was given to me as a gift.
by a student.
Here's a mole.
Yeah, the teacher I did my student teaching with after that's what he gave me. He was a really awesome guy. I learned a lot from him, but also a little strange. But he gave me a taxidermy mold.
Obviously.
He bought a taxi.
That guy's awesome.
You're just gonna leave the.
One of these, what president? I want to like tie like some fishing line to him one time and like pull him through the hallway.
Oh my gosh, that's awesome.
Like freak people out. Okay, anyway, so that's molarity, is moles per liter. Now, in terms of a lab setting, can I see 2 moles of something?
Not really.
No.
I mean, you could, but you don't really know what that looks like, right? So what we have to measure out in a lab setting are grams. Grams are what we measure, and then we can convert them into moles, okay? So let's try a problem here with doing that. So it says we want to know what is the molarity of a solution made by dissolving 23.4 grams of sodium sulfate in enough water to form 125 milliliters of solution. Okay, so visualize what's happening here. I have a scale. I poured out 23.4 grams. Okay, now what it means by enough water is that when you make a solution, the type of, equipment that you use are these very scientific looking things called volumetric flasks. Right, so we have lots of different sizes depending on what you want, cute little ones. Okay. These are used to measure one volume and one volume only, but with extreme accuracy. So, for example, if you want to measure out 1,000 milliliters, this is what you would use. I don't know if I'll bring it around, but there's a very faint line up on the rim. Can you see that? It's right above my finger.
Can't do volumetric flask.
Here you go, people at home. You see that? Okay. So these are made to measure that exact volume to, what's this one, 0.3 plus or minus a milliliter,
Oh.
which is very, very precise in measurement. Now, if I wanted to measure out 900 milliliters, would I use this?
No.
No, because there's no other markings on there, right? Like, I don't know what 900 is. That's why we use the graduated ones with lots of markings if it's somewhere in between. But when you make a solution, you want your solution to be as accurate as possible, otherwise it will mess up your experiment. And so that's why this is used. So what it's saying here is you would take your, so we need 125 one. I don't have one, so this was 125. You'd pour your salt in, then fill the water up to the line.
Oh.
Does anyone know why I wouldn't want to measure the 125 separate and then just pour them into a beaker? Evan?
Because it'd be bigger than 125.
Yeah, because the salt's going to take up some of the space, right? So it'd be technically more than 125. So you do the solid. Well, normally I put a little water in the bottom so it doesn't stick. Then I put the salt in, and then I fill it up to the line. Okay? Okay, so let's calculate what molarity this solution would give us. So molarity is, I'm going to just write it up here, is moles per liter. Since I'm doing a lot of math today, Landon, can you look at that iPad? Where's my really bright dot?
Right there.
Right where your hand is.
Right here?
A little bit up.
Can you see that X?
No. Very little up the left.
Okay, so if I avoid that X, it'll be okay.
You should just like draw a big circle around.
Yeah, it's a little more to the right though.
Okay, up a.
A little bit smaller and like
That's good.
to the right and up.
Up and right.
It's good
That
enough.
works.
Wait.
Good enough.
Just avoid that circle.
More is like, I just won't get close to that.
Give it like
Okay.
a ellipse radius.
Yes.
Okay, perfect.
It's
Okay,
more of an ellipse
so-
than a circle.
molarity is moles over liter, so we have to find two things and then combine them. So what I know is I know my grams, so take that and write that down. So take your 23.4 grams of sodium sulfate. And our first step is we've got to convert this into how many moles is this? So conveniently, they gave me the molar mass, 142. I'm going from grams, I'm going into moles. The 142 would go on the bottom. Plug that into a calculator and I got 0.1648 moles. This will get plugged into the top of the equation for the moles. Liters.
You need
What do I have?
milliliters.
Yes, I have milliliters. Whoops, 125. In liters, that would be
0.125.
0.125. So this will plug into the bottom. I'm just going to rewrite my equation over here. So to find the molarity, we have our moles, 1648, over our liters, which is 0.125. Dividing their calculator to get 1.32. Now your unit can be one of two things. You can just do a capital M, because that represents molarity. So we'd say capital M, sodium sulfate. Or you can write it like that, moles over liters. That's the same thing. When we talk about molarity, we use the word molar. So I would say that this is a 1.32 molar solution of sodium sulfate is what we just made. Questions on that equation or any of the math? Now, I'll be honest, I found this problem in our book to practice the equation, but it's kind of a dumb question. Because rarely in the lab do you just pour things together and then like, I wonder what concentration this is. Normally you know what concentration you want, and you have to figure out what you need to make it. So, same equation, just rearranged a little bit, okay? So this one says, a student wishes to prepare 2 liters of a 0.1 molar potassium iodate solution. We want to know how much we need to weigh out. Okay, so erase this, keep the same equation. Now this is what I do all the time. Before any lab, if we use a concentration in our lab, like last time we used 2 molar HCl, I don't have 2 molar HCl in my cupboard, so often I'll have to make it, if I don't have it already. So what do I know in this problem? What's given? Good, so I already know capital M is 0.1. Those zeros for sig figs. What else do I know?
The liters.
The liters.
Yeah, I know the volume I want. Okay? So we're trying to find how many moles we need to dissolve in it. Yeah, Evan.
Would we just like rearrange it like we did per nerd and just do ml?
Exactly. Yep, so we're just going to times it to the other side, right, to get x by itself. So in this case, x is going to equal 0.2 moles. Is that my answer?
No,
Why is that not my answer?
because you need grams.
Yeah, I don't have a scale that measures moles, right?
That would be pretty cool.
So we gotta convert. Once again, they gave me the molar mass, so I'm going from moles into grams. So the grams this time goes on the top. Times that through, and I got 42.8. Questions on that equation? AP quiz 3.7 has problems very similar to these two. So if you get stuck on one of those, maybe come back and review how you did these ones to get you thinking. Same equation, just used in different ways. So, good for now? Okay, let's transition away from math for a second and look at things from the molecular view of what's going on. Okay, so when we've talked about this before, that with ionic substances dissolve in water. Covalents sometimes dissolve in water, and then metals never dissolve in water. Does anyone remember why at the molecular level, why do ionic substances dissolve? Yeah, Taylor, what's going on?
Because they're like positive and negative, so the positive and negative parts of water like attach to them and like tear them apart, kind of.
Good, yeah, it's like when we play with our cool little water cups, right? The little molecules of water, little Mickey Mouses, can latch on to the positive and negative, right? So sodium chloride is actually Na plus, and the Cl minus link together, so those little water molecules can come and pull it apart. Now, because it can pull apart, and because they are positive, we give these things a very special name, and we call them electrolytes. Just so you know, Gatorade did not come up with the word electrolyte. It's always been there. They just use it as their catchphrase because it does have a lot of electrolytes. Electrolyte just means something that has broken apart into positive and negative things in water, which there's lots of things that do that. Okay? Now, here's the interesting thing, is moles are not an additive thing. If I have 1 molar solution of NaCl, once the salt breaks apart, I have 1 of this, whoops, little n, big N, and
Oh.
1 of those. Yeah.
The N and CR in the circle.
Yeah.
Ah, I erased my circle.
I was gonna say something.
so this is where, once again, if you think too mathematically, it can be really confusing. Because what we have here is literally this equation is saying 1 equals 1 plus 1.
Yeah.
So how is that happening? Like, what's going on? Why does that work in chemistry?
Because science.
Yeah,
Science.
Max.
That's what I said.
Because for each mole of NaCl, there are, like each molecule, it's counting molecules, there's a mole of NaCl molecules, and in each molecule, there is an Na and a Cl, so there's a mole of each.
Yeah, right? Perfect way of saying how it's not that. This is counting them together. Now we're counting them separate, which you still have 1 and 1. The way I kind of think about it is the number doesn't cut in half because the molecule is cutting in half. But it can be a very confusing thing where a lot of people want to divide by 2, right, when things split in chemistry. But that's not how moles work because mole is just a counting number. Okay? To see if we've got it for 2 smiley faces, with your table buddy, fill in the blanks for the next example. Ready, go. So what would be the blanks for sodium sulfate?
That
Yeah.
makes sense to me, yeah, okay. I mean, if it's not, that'd be really weird. Yeah. Maybe 2.0. He's up there, she got 2.0, so I'm just gonna add.
Set your pencil down when you're done.
Did you figure it out?
Someone on this, I think it was this row. Is this in here?
Wait, I think it might be. Yes. I was looking for this
Imagine
yesterday.
forgetting your assignment.
Oh.
I can't believe you.
Okay, everybody ready? If you have 2 here, you can have a smiley face.
Let's go.
And a 1 here, you can have a
Wait.
So let's take a look here. So we have Na2SO4.
Oh,
I didn't even read it.
oh, there would have been parentheses. I am quite. I feel so stupid. Okay.
When this breaks apart, it's breaking apart into sodium and sulfate. So first off, why does sulfate not break apart into more things?
It doesn't want to.
It doesn't want to, yeah, it's true. Why does it not want to though?
Because it's in a covalent bond.
It's a covalent bond, yeah.
Like he
So
said.
these are covalently linked to each other so they don't get pulled apart. Gavin Taylor have a smiley face for coming together with the answer.
Yeah.
Now, the sodium, I end up with
Why is it
2 of them because they break apart from each other. Okay, keep in mind in chemistry, small numbers mean they're linked, big number means they're separate. The reason why the 2 sodiums come apart from each other is because they're both positively charged, right? So they get separated from them. So in a sense, our math equation here is 1 equals 2 plus 1.
Yeah, science.
Yes. Questions on how things split up? Okay, let's jump back to the math side. Okay? So one way you can make a solution is what we just said. You take a solid, you measure out the grams, put it in your flask, fill it up with water, stir it around, you made a solution. Another way you can make a solution though is actually by taking a solution you've already made and diluting it down. For example, what was the molarity we used for the lab last time? 2, right?
Because it's two.
I don't buy 2 molar hydrochloric acid from my chemical distributor. I choose to buy 12 molar hydrochloric acid.
Wow.
Because what do I have to add to make it turn into 2?
Water.
Water. So it's a lot cheaper for me to buy a high concentrated amount and add my own water to make whatever I need. Okay? Now with this, the key concept here is if I have 12 molar hydrochloric acid and I add water to it, am I changing the amount of moles of HCl in there?
No.
No, I'm just adding water and spreading them apart. So the concept of a dilution is that the moles before will equal the moles after. You're just adding water, okay? So there is an equation that helps you with this connection process, and it's one of the 5 formulas that's not on your formula sheet.
Great.
So you either memorize it, or
Hope it
by
doesn't show up.
understanding this, you can kind of come up with it if you were to forget it. So the idea is this: if I take the molarity of my concentrated amount, so I'm going to say M1, okay, and I multiply it by the volume of it. Now I'm going to rewrite it below just to show you how this equation is working. So what does M stand for?
Molarity.
Molarity. What is molarity? What are the units for molarity?
And
It's mass, moles over volume. This.
Okay, which is, yeah, moles over volume, moles over liters. So if I take moles per liter and times it by a liter,
That's just moles.
it's just moles. So that's how this equation is working. It is literally saying the moles before will equal the moles after.
Wow.
Wait, so why does that equation even exist?
Yeah, why does that matter?
So, here's how it works. I have a 1 molar copper sulfate solution. Okay?
Alright.
For our lab, let's say I want to make a 0.1 molar solution. How much of this do I need to make that? That's where this equation is used.
That makes sense.
So it helps us know what to use in the change. That make sense?
Yes.
So, good question though. Okay, so let's try it.
I know. So these are rare commodities.
Okay, so from the problem, once again it tells us, and you can label them like concentrated and dilute. I just like using numbers because it's easier, but it's the same concept of before and after. Okay, so we know our concentrated molarity is 1. What do I want my concentration to be? 0.1. How much of my diluted one do I need for the lab?
250.
The question is, how much of the concentrated do I need to make that amount? Okay? So, get our equation, M1V1 equals, oh, that's the bad spot, right there. The thing I'm solving for is
V1.
V1, so if I want to get that by itself, move N1 to the other side.
It's just dividing.
Okay, plug in all of our variables, so 0.1 times by 250 over 1. Plug that all in, we get 25. Yeah,
We need to
Landon.
change it, the
Okay.
milliliters to liters.
Oh, great observation, Isaac. You can, you actually don't have to.
Because they're all in
As long as it's the same on both sides.
Yeah, because it's a proportion equation,
Okay, that makes sense.
if you change it to liters, your answer would be in liters. In this case, we can keep it in milliliters and our answer is in milliliters. But great observation, because in other cases, you have to change it over.
Isn't, the molarity moles over liters?
So the way that it works, right, so molarity is moles per liter. If my volume is in milliliters, what would I be doing to get it to liters?
Divided by 100.
It'd be divided by 1,000, right? And in a sense, since you're doing the same thing on both sides, it kind of like cancels out. So that's why it will still work mathematically without converting to a liter, is just because it's a before and after equation. But if it wasn't a before and after, if it was just like straight up molarity, you've got to go to liters. Great observation. Or same thing like with pervnert, right? Like you have to convert that because it's just a one-step type thing. So does that answer your question?
Yes.
Yeah, great question. I forgot to mention that. Any other questions on that? Does that make sense to everyone? Okay, so we just found our answer of 25 milliliters. Okay, now here's what I want you to come up with your table, buddy. You don't have to write it down, you can if you want to. But I want you to come up with the instructions now. We did the math. But what are the actual instructions for making this new solution? Right? So if I'm standing up here, you're going to tell me what to do. What are you going to tell me to do? What am I going to use? What am I going to grab? What am I going to measure to make what the question is asking? Okay, turn to your table, buddy, and come up with an instructions of how to make this solution. Ready, set, go.
Wait, so that means they have 25 milliliters, like a 25 milliliter solution, and we need to make it
So you measure out
so we need
25 milliliters.
We just need what's over 25 milliliters.
Then,
Or just
okay, and, yeah, and then you pour
because this is what
enough
this
water in to make it
So we found out that the first solution was just 1 over 25. We want it to be 1 over 200. And so 25.
well, yes, but you just use one of those things and do the stuff. I think, right?
When you have to start the molar,
Jamie's really slick with it. She goes, okay guys, think about
Yeah, yeah, I like myself.
Okay, anyone willing to share the instructions? Okay, now you're going to do it like, I swear this is like, I don't know. Elementary school, you always have that assignment where you have to write a list of instructions for someone to like make a peanut butter sandwich.
yeah, it's
Oh.
You know what I'm talking
on
about?
the tray.
That's what we're going to do right now, but with chemicals. Sounds safe, huh? Okay, Evan, what am I doing?
You're gonna have like, wait, is that one already the first like?
This is
thing?
the 1 molar.
Okay.
Yeah.
So you're gonna take 25 or you're gonna pour 25 milliliters,
Okay, I forgot to grab some. So we're going to pretend here. 25
Okay.
milliliters.
and then you're gonna add 225 milliliters of water to it, and then it makes your diluted.
Ooh, you're really, really close. Have a smiley face.
Okay.
What's he missing, Isaac?
You're supposed to fill it up with water until you get to 250 milliliters.
Good.
Like
So
you
we
have
actually
every-
don't measure the liquid separately.
Oh.
And it's kind of the same concept you said before, and it's weird though. That volume is not always 100% additive. Okay, you can have 50 mils of one and 50 mils of another, pour them together and not end up with 100.
What?
Ends up with 90, and you're like,
You got it? What if you end up with more? That'd be fucking
Now if you end up with more, I don't know what's happening.
Yeah.
Well, why would that be? Why could the volume go down once two things mix?
Oh.
Yeah, they like each other. They're intermolecular forces, right? Pull them
Surprise.
closer,
So awesome.
so they actually take up less space. So, Isaac, have a smiley face for that. So that's where we would use one of these again. We pour in our 25, and then add water until it gets to the line. So, questions on the math and understanding what dilutions are?
Yeah, say like what you would do one more time.
Yeah, so you would pour, so the thing we calculated,
Yeah.
so I poured 25 milliliters of my concentrated solution
Awesome.
into my volumetric flask. So I'd use like a graduated cylinder to measure out 25 mils. then I would add water to fill it up to 250 or whatever we're making. 250.
I get it now.
Good?
We get it.
Okay. If anyone wants a really exciting TA, sorry if you're a senior, but if you're not a senior and you want a good TA job, that's what I have my TAs do all the time is make solutions for me. 'Cause we need them for like every lab. And so, say, here, go make this, go make this. So, okay. Questions? Okay, let's go back to this concept of electrolytes a little bit. Okay? Now, once again, the reason why scientists call them electrolytes is because they conduct electricity. Okay, this right here is distilled water. We've talked about this before, but what is distilled water?
Oh, it's like pure water.
Just H2O, right? There's nothing else in there. Now, this is slightly expired, so it might not be perfect.
Expired
Expired water.
No, it really is.
What?
Why would distilled water jugs have an expiration date?
because they like dissolve the plastic and it gets in the water.
Yeah, because over time, things can get into the water, which makes it not distilled anymore.
Wow.
So,
Imagine.
yeah, so this expired last,
I was like, bro, can we drink some water?
but it should hopefully still be okay.
Does distilled water taste good?
So if I take my light bulb and I stick it in distilled water, it doesn't conduct
No.
because there's no positive or negative things to make it conduct. If I add an electrolyte, oh, that's a lot of electrolyte.
Well, I mean, there's power.
Okay.
Right? So you can get it to conduct.
Salts are batteries.
Now,
No, it's plugged in. It's providing the electricity.
yeah. This so
Oh,
don't
that's
like-
just
Yeah,
the
no,
current.
oh,
Oh,
you
I was
guys
like,
are
I was like, what?
Right?
The
ocean is the energy source.
Yeah, you
You're just like, what's wrong with you?
You like have a phone book.
Yeah, so it's not making the energy, it's just conducting the energy. So, on the reverse, a non-electrolyte is something that doesn't conduct because it doesn't have positive or negative things floating around. Okay, so we're going to draw two pictures, one of molecular views, one of an electrolyte and one of a non-electrolyte to understand what's happening there. Yeah, and it,
This is kind of like off topic, but like, is that why, like, if you put like a toaster in the bath, like, oh, okay.
yes, because the electricity from the toaster will travel through the water. It's also why they make you get out of swimming pools when there's a lightning storm.
Oh,
You ever watched a video of lightning strike?
that makes so much more sense now.
Yeah, it's really cool.
That's the question. That's the real science question is if I was in a pool of distilled water,
Well,
Yeah.
yeah, that would
We just
expire
need to get a
now.
kiddie
I would
pool
love
at this
to.
Yeah,
point,
the
'cause we have a
expiration
pool of
date, the
oil.
price would be like
yeah, it'd be a little tricky. Well, and also we have so many salts on us. As soon as you got in,
We could probably.
Okay, shower with distilled water and then get into the distilled water.
Or we could just boil ourselves.
and then get shocked by lightning and see what happens. Sounds like a good plan. Actually,
Is chlorine electrolyte?
yes. So electrolyte is any negative or positive ion. So yeah, so the chlorine in a swimming pool makes it very conductive. Yep.
Ah.
Oh.
Good to know. So, you know, toaster and pool works better.
I think it dropped on the ground.
Okay, so let's first do, what's the example I gave? Sodium sulfate again, I think? Okay. Alright, so let's write the equation again on that line up above. Okay, so there's sodium sulfate, the little s means solid. Okay, so this is as a solid, I haven't dissolved it yet. The arrow's indicating the change, so now I'm gonna pour this into water. Okay, super high fancy experiment here. Okay, because it's ionic, it splits up, just like we did before, into 2 sodiums and 1 sulfate. Now that it's dissolved in water, though, we don't classify as a solid anymore. And you remember the little code we used?
Like a solid
There it is, AQ, aqueous. So aqueous means dissolved in water. So notice that water is not in the actual equation, but it's implied by putting AQ. Now, let's draw it. So we have 2 sodiums.
Definitely fix it if it works.
Say that again.
Are we going like the?
We're just gonna draw the after picture. Yeah, so we're just drawing the aqueous one. Now, sulfate is gonna stay all together. So I'm just gonna draw it like this. Technically, we could draw the Lewis structure for it,
That's too much work.
but we don't care about that right now.
No time.
Now, what's the water doing here?
It's
It's like surrounding it.
Good, so they surround them in a very particular way.
Yeah, the negative is
Good, negative to positive, positive and negative. So the face of Mickey Mouse
Oh my gosh, they're leeches.
attaches to the positives. Now keep in mind, if we could see this in 3D space,
they'd be all of it.
right, it would be completely surrounded.
Oh my gosh.
It's a
Evil.
trap.
And then the ears attached to this side because they're the positive. So if we could magic school bus into this beaker,
No.
that's what we'd see. Be very excited.
Dude, what if the water started attacking us?
The water started attacking the bus.
What if we were negatively charged?
I feel like that's what would happen if that was an episode. So. Okay, questions on electrolyte molecular view. If you so happen had to draw a picture like this on your own on the test, let's say, could you do it?
You know.
Yeah.
Yeah.
So given this only, can you turn that into a picture?
Yes.
Just drop some
I can
fingers.
try
It wouldn't
really
look good, but yeah.
Any questions?
Yeah.
Okay, let's go now to something that is not an electrolyte and look at the difference. Yes.
Oh, I remember this from Mr. Shaw.
Okay. C6H12O6 is glucose, which is a form of sugar. There's lots of sugars, but it's the simplest one.
Glucose.
Okay. Now, if I got some sugar, poured it in water, does sugar dissolve?
Yes.
Yes.
That's how you make Kool-Aid, right? You dissolve the sugar in the water. But the difference is, at the molecular level, the pieces don't come apart from each other. So in terms of an equation, we just write it as C6H12O6 aqueous. Just to say, hey, it's now dissolved in water, but the individual pieces haven't broken apart. Okay, we're going to draw the Lewis structure for glucose to talk about here.
What?
But keep in mind that you would not be expected to draw this structure on your own. I just didn't print it in your notes, so you're going to draw it.
Yes, wait.
Yeah.
It's a hexagon.
Okay, that's it.
Last year my bio.
Oh, no.
Yeah, no.
Okay, so there's 6 carbons.
Yeah.
So draw this with me here. So 6 carbons all linked together.
Double bond.
Okay, got a double bond O, H on this side.
Of course.
Okay, we then have off this carbon, you have an O to an H,
Yo. What?
an H off the top.
Ah, oh my god.
Okay,
I think I could try something.
This is a lot.
I don't doubt you guys could do it on your own. Just know you won't have to.
I doubt I could.
I don't think we can do this on my
Hardcore
own.
doubt.
Ow.
So the pattern kind of alternates for like the OH, OH, OH.
Oh. Oh, I could do this on my own. Just like a little.
Okay, now that she's made it, I could probably do it.
You know, if there was just a picture in front of me, I could draw it perfect.
Perfect.
You know?
Yeah, you think so?
Someone just showed me how I could do it. Okay,
You know,
sorry, I'll give you a second to finish your drawing.
Oh.
I'm so proud of this, and
This
I don't
oxygen
even
is
work for it.
Oh wait, sugar.
It's okay, no one else has to know your Go home and show your mom, look what I did. Okay, now here's the
All
question.
chemistry today
The
figuring
fact
out.
that she said sugar was sugar.
So, sugar, we just said, does dissolve in water. Do any of these bonds get broken though when it dissolves?
no.
No. So what makes sugar dissolve? It's not breaking apart, and that's what's going on there.
Would it probably just be that all the waters are attaching onto the molecule, they're not strong enough to break it apart, but they're breaking it from the other molecules that are holding it together?
Perfect. How does my base that? So first off,
Yeah, nice.
okay, and test. So keep in mind to really draw sugar, we have tons of these, right? Lots and lots and lots. Like even in a tiny grain, you're gonna have zillions of these things. So when it dissolves, it's that this is breaking away from other sugars. Now here's the next question. Don't say it out loud, so everyone can think for a second. What forces is water using to make it dissolve? Don't say it out loud. What type of forces does water use here? Because in this case, it's using the fact that it's positive and negative. What forces are going on here that allow it to dissolve? Raise your hand if you have an idea.
This is just a total
I like very slowly. Don't be shy, it's okay. Okay, Landon, what are you thinking?
Magnetic forces.
Ooh, house my face, yes. Let's get more specific.
Oh, no, probably not be that.
Hydrogen bonding.
Oh, actually, it might be.
Yes. So water, a little water molecule,
Wait, what was the answer?
Hydrogen.
okay?
Wait.
Correct answer is hydrogen bond. Okay?
We're not going to say that. Don't flatter yourself.
This right here, everybody,
I was gonna say.
is a hydrogen bond, right? So you gotta have a knob sandwich, N-O-F, with an H in the middle. So you have O to H to O. Right there, the water, and there's lots of sites for it, right? It can hydrogen here, 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 here. The water can surround the molecule and pull it away from other molecules. But like Max said, it's not strong enough to pull the molecule apart from itself. That's why it's a non-electrolyte, is because there's no positive and negative charges. It can dissolve, but it doesn't heat up. Questions on that? Now, if, hypothetically, a test were to give you a picture of this and told you to draw a hydrogen bond on it, would you draw that?
I mean, now I would.
Yeah.
Like 5 seconds ago, I would not have drawn that.
Now tell me, don't say it out loud, but give me a thumbs up or thumbs down. Would this also work?
I don't know.
Thumbs up or thumbs down, does that work for a hydrogen bond?
Oh, it's not a sandwich.
They're not.
No sandwich.
But then I think you said something about it being in between. So.
Wait, I'm just thinking about
It
this.
has to be a sandwich.
You know, I'll give it a sometimes.
No, sometimes.
Just,
If you had thumbs down, you
it's
never
the
said
oxygen,
it.
like, I'm a bond.
Right? You gotta have the sandwich of both things, right? Carbon is not electronegative enough to cause that hydrogen bond to form.
Oh.
Yeah, Gavin.
I think at the end of every class, we should clap like it's a TED Talk or something.
Yeah,
Because
we
I'd pay
should.
way more attention if it was like a TED Talk kind of thing. I don't know why.
So
I just-
tell
that's
me you'll
just a
pay
thought
more
I had.
attention if we just clap.
Yeah, just
Yeah,
at
just
the end
at
of
the
the class,
very end of
like,
class.
think about, walk out of your little circle and just, we all just clap.
End
like
it
this.
with thank you.
Yeah. And you would feel awesome. You would feel really cool
Yeah,
too.
just say,
This one
thank
is
you.
such
and we are-
a talking.
Sure, we can start doing
Yeah.
that. We can do it before we're taking on the screen, huh? Is that why you're thinking TED Talk?
I think we should do that.
Man, now I feel like I gotta like come up with other things to add now. Or I don't know, come with like a little microphone.
Yeah.
Yes. So.
Okay, any questions about non-electrolytes? Okay, I have a question for you and your table buddy to solve now.
Oh,
Choice.
AP Chemistry practice multiple choice question.
evil.
Ready, set, go. You can talk to your table buddy if you
Oh,
want.
this thing? 3.8? Oh no. One year solution. Student combines the solutions by pouring them into a larger previously empty Z enters the formula with plus 16. Assuming that volumes are added, which of the following sets of beakers could be represented?
So X and Y.
Volumes are added, which of the following sets of solutions?
So, this is more negative.
I'm so confused.
There's so many numbers.
Previously empty beaker and observes the formation of a white precipitate. Assuming that volumes are added in, does that mean? Which of the following sets of solutions would be represented by the
Once you have an answer, circle it on your paper.
Oh, wait. I think I understand.
no, it's one.
Let me see.
So it has to equal one.
Oh, yeah.
Okay, wait. Let me just think for a second.
But,
I think I understand.
so we need to figure out what these things are. So there's
No, I
A,
still
G, N, O, 3,
I have no idea. I just.
M, G, Y.
So we know that the AGN of 3 has to be 2 points.
Yeah. Because
Now,
N
in
of 3
case you're ignoring it, the pictures are there for a reason.
So,
Think about that.
A, G,
And if you haven't thought about counting things in the picture,
Yo, it's funny because this is.
but it's like covering it a little bit.
oh, and put it on yours too.
Yeah.
So you can't see, so.
Yeah, I think we get a freebie on this one.
We should get free 5 smiley faces because we don't know.
Yeah. 5
Imagine being on a test and having
No, 5 total, and we divide out amongst the
Which would
class.
mean that it would stay the same.
I don't know how many there are.
Then that would mean that these negatives disappear.
Same with the positives.
I just confused.
Why?
Because the positive and negatives combine, so you get AGC less.
I don't know why I'm telling you my strategy. That's what I think.
So, I think,
64.
but you have more
It's
than
just my plan. Deal?
because you're equal to the same.
Okay.
Oh,
Creating a new one.
so like the water breaks apart these things.
I know.
So it would be 2 because there are 2 finishing things, right?
I'm sorry, I know you probably already know this, but I
So
just know
that
this, okay?
one.
So,
But then
Maybe,
why?
but then
let's see.
I don't know.
Maybe it's
Wait, how much is?
Okay, I'm gonna give you 30 more seconds.
I think you should give us a hint.
I did.
You did? Oh, look at your picture.
Look at the picture and count things.
sorry, I can count. See,
No.
I'm super good at guessing.
It's.
So
Guess sometimes I think, now test.
I think it would be A.
I guess it's C.
Okay, take a guess in
Because
10.
you're keeping it from here.
Wait, then that's the wrong answer. I guess B then.
5,
Okay, I was gonna switch my.
3,
I know A is
2, 1. Take a guess. Put your pencil down.
Okay.
I circled B and C.
Okay, first off, this is just an internal judgment. If you feel like you honestly gave your best effort, you can have a smiley face. No,
Yes.
100, you got it right.
I mean, I looked at that for quality, like,
I looked at that for
Okay, show me, put it underneath your chin, and don't look at others. Show me your choice, A, B, C, or D. You should never leave a multiple choice blank, so you should have some. Might as well take your chances of 25%.
The paper doesn't judge me though, I don't know what you'll see.
No judgments here. I have short-term memory loss, so I'll forget what you put anyways by the time we leave.
What?
Okay, looks like some of us are united. Okay, if you put C or D, you can have a second smiley face. Oh,
When in doubt, guess C every
yeah,
time.
let's find out which one is the real one, and then you'll get a third smiley face. Okay, so first off, anyone who picks C or D want to share their logic of why they picked it?
Dude, guessing.
That's not logic.
That's pure logic.
Okay, Gavin, let's hear it.
C is the most common correct answer in multiple choice.
Statistics told me to.
Because
I
C
mean, I guess
stands for
that's
correct.
I'm not gonna put any C's on our next test. It's actually
Don't even say something like that, because now I think they're all gonna be C. You can't do this to us.
I actually don't, I just make tests and then I solve them to make my answer. So, because I don't make any of the questions, I just find questions. So, I don't like choose, like, hey, this is gonna be A, B, anyway. Okay, anyone else have a logic they wanna share? Zach, let's hear it.
I didn't put C, but I think I have a logic why it works.
Yeah.
So they're additive, and which means they're gonna combine, which means the volume's gonna be less.
Ooh, okay. Kind of on the right track. So first off, let's break it down like this, right, buddy? So I picked this question for a variety of reasons. Number one is I just want to remind us how multi-step AP questions are, right? AP multiple choice questions are not, hey, read and answer, right? There's so many pieces to it. So the first step, here's how my brain goes. I'd say, okay, well, what is molarity? Moles per liter, right? So moles are a counting thing. So if I come up here and count in AgNO3, so that means it's separated, but if I group them together and I count, there are 10 molecules in that beaker. So if you draw lines between one positive and one negative, you end up with 10 molecules. In this one, it's MgCl2. You've got to pair up 2 negatives for every 1 positive. If I pair that up, I end up with
Is that what these small things were?
Yeah,
Oh.
You just looked at
I think you can still do it. Because look, because 1, 2, 3, 4, and then you have 2 negatives left, so there has to be a positive.
Yeah, that's what I was
I didn't even
I do
notice
agree,
that.
normally it wouldn't be cut off on the AP test, they won't do that.
Just like, you have to guess, and hopefully you'll get it
Okay,
right.
so first off, that's how I get this 2-to-1 ratio, is by counting the moles.
Oh,
Does everyone understand that?
I get it.
First off. Okay, now the second half of the equation, if I count in this beaker, so let's do it together. So the thing that, so notice AgCl is in this pile, so it's not up there, because it's a solid. So I'm just counting MgNO3 2. So that means 2 negatives for every 1 positive. So if I do that, I end up with 5 again. But the answer is D, not C.
Why?
Did anyone put D?
Because it's 10.
I just
So you
put
divide
C.
it, and it's 1.
But it's like
There you go, Frank. Have a smile face for that light bulb. Okay, everyone listen to Brycean. So the proportion is 2 to 1 to 1. But what is molarity measuring?
It's moles over volume.
Moles per volume. What happened to the volume of this container?
It
Oh.
Doubled, so the molarity cuts in half. Now once again, it's okay today that you didn't get it, but it's just to remind you once again, all the different pieces that are part of an AQ question, but also to keep it simple, right? My first thing whenever I'm problem solving is I just say, okay, well, what am I asking here? Molarity. Okay, what is molarity? Right? And then just keep connecting the pieces, and then we'll get better at problem solving as we go. So, questions on that question though? Yeah, Gavin.
So I get the 2 to 1 to 1 like in the third number is like half, but then there's the 2 and at the end. Is that just the stuff at the bottom?
This right here?
Yeah.
Yeah, so that, and it should be, it didn't print well, it should be subscripted.
Okay.
So that's just part of how that thing is bonded.
Oh.
So it's saying that in this compound, there's 2 nitrates for every 1 magnesium.
Oh, I thought it was saying there were 2 moles of the ABCL.
Oh, like you thought it was like,
Yeah, I was trying to figure that out in my head.
like you almost like insert a space here, like
Yeah.
one of those and 2.
Yeah.
That's a good observation in the sense of, or important to recognize that solid things don't have molarities. Because to have a molarity, you have to be dissolved in something else. So I can totally see how you could read that though, like if you just put a pause there in your reading. So,
Yeah.
any other questions on that for now? Okay, last concept here is this thing, we've actually touched on it before when I did, I think it was the very first day of the unit when I had the oil and the water in the graduated cylinder and we dropped in the food coloring. Everyone remembering that?
Oh.
Yeah.
So
Alright, what did the food coloring do?
it didn't, or it separated.
So it stayed together in the oil and then what did it do when it hit the water? It spread out, right? So we often, or one way you can talk about it is we say like dissolves like. It's like a catchphrase in chemistry. Things with similar forces can dissolve things with other similar forces, right? So if something is polar, it can dissolve other polar things. If they're opposite in forces, like oil and water, then they won't mix or they won't dissolve with one another. Okay? Now, a good sign that you understand this concept is if you understand the comic. If it kind of makes you giggle inside, then that's a good sign you understand what I'm trying to say here. Okay? Now, it is important, we pointed this out before, do oil and water actually, are they repelling each other?
No.
No, water's just attracted to itself.
Yeah, water just likes itself.
Like that.
Oil just is kind of there, right? But they're not actually pushing away from one another. Okay? So with this concept of like dissolves like, here's just another little demo for you here. This right here is actually some pretty cool paper because it is soluble in water. Normal paper will get wet and soggy, but this paper, ready, watch this, in the water.
No.
Wait, what?
Where's my, what can I use to stir it with?
When you stir a paper.
Is it like that edible paper?
So it's completely
Oh, the
It's
ink.
just the ink.
dissolved, yeah. So the ink doesn't dissolve, because the ink is not water soluble,
The heck?
but the paper is. Okay, so let's look at our practice problem here. Okay? Of whether or not things will dissolve. Okay, let's skip to number 3. These two are a review from before. We'll come back to those, but let's do number 3 since that deals with the dissolve. Okay. So the question says, identify for each of the above substances, would they dissolve better in water or in carbon tetrachloride? So imagine I have 2 beakers here. I want to know if I dump that into each beaker, which one will it dissolve better in? Okay, so first step whenever any question deals with dissolving is you've got to look at what forces does it have. So what forces, I'm going to write it up here, what intermolecular forces does water contain? Or I guess we could just go, is it polar or is it non-polar?
It's polar.
Okay, so H2O is polar. Carbon tetrachloride is this.
I'm going to assume it's not.
And you can kind of assume, yep, it's the opposite, right? So, if something is going to dissolve in something else, the forces are similar to each other. So our first structure up here, don't say it out loud, thumbs up if that structure is polar, thumbs down if that structure is non-polar. Okay, if you're giving a thumbs down, have a smiley face.
Dude, all of a sudden I was like really worried.
So CH4 would dissolve better in carbon tetrachloride because it is also non-polar. Okay, sort the other two for me real quick. Yeah, we skipped to number 3 right now. I'm just writing above this and below. So put CH3F and CH3OH, decide which cup they would dissolve better in real quick, and then we'll check them for some smileys.
Can we work on this with,
Yeah, you talk to your people, buddy.
Okay, so we have CH4. And then, okay, the CH3F, would, that's definitely 100%.
Yes.
So that one would be
CH3F. And then, the other one is also polar, right? Because the hydrogen is
The first one would be polar, right? Because like the first, because those two middles is like reciprocity. So the first one with the C in the middle, that would be polar. The second one would be bent, which is also polar.
So how, we would probably write CH3O.
But then I don't know, because there's so much other stuff going on.
Think about it. People often say water or oil. How would you fix? Do you disagree? Would you agree or disagree? You just don't, yeah.
Because, so like, this takes a best which is this body. Because these would force these down. Right? And then always just more like so I feel like the electrons would go there. But then I think I'm
you don't have to wake up if you don't go to sleep. You know this. If you don't go to sleep, you also can't remember anything.
Well, guys, here's the biggest question I've ever thought. If we legalize all crimes, crime rate will drop to 0. Yeah. So I vote.
And the country would also be screwed.
No, I don't know what you're talking about. There'd be no crime.
Thank you for the TED Talk.
That was awesome.
We'll check those two problems when you come back on break.
Thank you.
Thank you for listening to my TED Talk.
I guess the TED Talk's not give you homework, is that why you wanted to do that?
Oh, yeah. Yeah.